No, I think good.
It's good, right? So basically, we said we have latch, and this is the first attempt of actually building what? Building the sequential elements. Sequential elements. And the sequential element, that means is actually tied to the time. And we said where is the time as? The time is the clock. And the clock came from the crystal. And the crystal produced the shape of the signal, which we call a train of what? Pulses. This train of pulses, it has a unique configuration. It's basically, every single one, it has a size of t, which is, they call it what? Duty cycle. Then this little one, which is the on the cycle, it's equal to the off on the cycle, is equal t divided by 2. So the t on is equal t off equal t divided by 2. Then we define a factor, it's called clock rate or clock frequency. So clock rate is equal to the clock frequency is equal 1 over t. And we define the unit used for this as Hz, which is hertz. And then, this Hz can be K, M, gig, whatever, right? It can be Hz, it can be KHz, it can be MHz, it can be GHz. So Hz is the unit. KHz, that means 10 power 3 hertz. Then mega, 10 power 6 hertz. Then, giga is 10 power 9 hertz. Right? Then the time, we said it can be by second, millisecond, microsecond, nanosecond, or picosecond. Right? So millisecond, 10 power minus 3 second. Micro, 10 power minus 6 second. Nano, 10 power minus 9 second. Pico second. It's 10 power minus 12 second. So far, so good?
Yes.
Everybody aligned with me? Should I write it again? Somewhere else in the middle of nowhere? Here. Yeah, here. Time. Second. Millisecond. Microsecond. Nanosecond. Picosecond. Unity. MS. Unity microsecond. Unity nanos. NS, pico PS. How can you convert it to second? This one, 10 power minus 3 second. This one, 10 power minus 6 second. This one, 10 power minus 9 second. This one, 10 power minus 12 second. Right? But we are also having F is equation of 1 over T. So F, it can be hertz, it can be K hertz, it can be megahertz, it can be gigahertz, it can be whatever you want. It can be terahertz. Terahertz. So from hertz, gonna be what? 10 power 3 hertz. Then this 10 power 6 hertz. Then this 10 power 9 hertz. Then this one is 10 power 12 hertz. Okay. Also, we give some information about the clock, more than just like the time and the duration. We said that the clock has two different things. It has level and it has what? Edges. Level and edges. Do you guys agree? Edges We have positive edge. We have negative edge. We have positive edge, negative edge. You guys agree? Also, we have what? Positive edge can be called as rising edge. The negative edge, we can call it what? Falling edge. So this same, just two things are the same. Everybody agree? Then where are those located? Before the level, we have the high level, we have the low level. So we have high and we have low level. Okay, high level, low level. Positive edge, negative edge of the clock. Then we have here the clock. So, here's the clock. Right? So the unique in this is the high level, this is the low level. Then this is this part, the line, the vertical one, right? This is from the low to the high, so this is the positive edge. While this one is from the high to the low, so this is actually what? Negative edge. We mentioned in the documentation of the last lecture that there is devices will be performing on the positive edge, there is devices will be performing in the negative edge. Do you guys agree? So the device like in flip-flop, it has what? It has here the input Q complement, and then we have this line like this. This is my clock, and that means this device is working in what? Let's say this D. So this basically, this device actually is an example of the D flip-flop, and this D flip-flop working in a positive what? Edge. What does it mean? Every single output will be coming from the input, every single positive edge of the clock. And then another example of the negative edge. So basically another device, maybe you can do like this. This is S, this is R, and then we can just go like this. We can make it in the middle like that, and then gonna be the clock, and we just say this is Q complement, and this guy is SR flip-flop performing in the negative edge. So SR flip-flop in the negative edge. There was other books like one was talking about, and instead of the circle here in the middle, it can be somewhere else. So basically I can clean it up like this and clean it up like this and make it like that. So that's actually also negative edge of the clock, right? Then we said every time in the truth table or anything I would like to mention clock, I can make it like this. That's a sign of the positive edge, and when I do it like that, that's a sign of the negative edge. So everybody on the same page? Everybody understand what I'm saying? Is it clear to everybody?
Sounds good to me.
Rest of the nation.
Yep.
Sounds good?
All right.
Yay. Okay. Now we said in the flip-flop, we are involving time. And we said, the flip-flop is a little bit different than latch itself. So the flip-flop, it has three different tables. Somebody was asking, right? Somebody asked? No, everybody said yes. Okay. So we have truth table. We have a characteristic table, which some people call it a state table, and some other have called excitation table. So every single flip-flop, it has just three different things. Everybody agrees with me? That's basically what I mentioned before, right? Sounds good. Everybody agree with me, or you guys are not agreeing with me?
I'm kind of waiting to see an example.
I'm gonna show you the example. So how many flip-flop do we have? We have 4. So we have SR flip-flop. Then SR flip-flop didn't solve the problem that from SR latch. So SR flip-flop is based on SR latch. Okay? It didn't solve the problem that we have one state is what? Unused. So this still have unused state. Then people came and say, this is not fair. We have to find a solution. And they came into something that's called JK flip-flop. JK flip-flop removed this unsigned state, but they actually made a problem which is called what? Race condition in this state. Okay, so they cause a problem is called race condition. Then people came and say there is modification to the race condition and they fix it. But they came into a very nice conclusion. If you take part of the JK flip-flop, you can build something that's called D flip-flop, which is data flip-flop. Then if you just take the race condition by itself as a state, that means that state you isolated, you're gonna build something that's called T flip-flop. What they call a transition flip-flop. Then those are the 4 elements used in the sequential circuits. As a beginner in learning this, what you need to know everybody's story, how it works, how can you configure the 3 truth tables of it, how it actually can combine one from the other, you make implementations of it using gates, and then in the top of that, how can you move from one to the other. If you know that, you just close this area of the flip-flops. Then you will move to the next stage, which is the finite state machine and how to use flip-flops and all of this extra stuff. So far, so good.
Yeah. Wait, next to JK flip-flop, does that say race condition or
risk condition? Risk condition. That means the condition that, it was unused, now it's used, but it's causing a problem.
Okay.
But then, but it's still working,
Yeah.
Okay. Sounds interesting, right? So let's look at how we start talking about, I remember last time, about if we would like to add enable, if I would like to add enable to the latch, right? I came into a conclusion calling that, there is like an extra NAND if you are a NAND latch and so on, right? You guys remember that? You guys remember or you don't remember?
Yeah, that's when data transmissions when enables high.
Yes, do you remember when we came into this latch and we said this is Q complement, and then we came into this one, and then we said here is NAND, and then here's another NAND, and then we came into like this, and then this is S and this is R, and then we came here and say this is enable, right? And this is NAND latch, right? And then we start tracing the NAND, and then we came here to something that's called a star, R star, and from there we move forward to the normal latch. I would recommend you to look to the previous lecture. Okay, I don't want to add too much redundancy in this. Sounds good?
Sounds good.
Okay, so now let's have fun with the first flip-flop, which is called SR. So SR, it's pretty much is at latch, but it has a clock. Okay, this is the definition. So what is the symbol wise of SR? Is basically S, and here is an R, and here is the Q, and here is Q complement, and then we have here the thing in the middle, and I will just have a different color here, and I call this clock. So this is flip-flop type SR, and is it positive edge operated or negative edge operated?
Positive.
Positive. So gonna be here positive edge operated. Sounds good? So far so good. It looks really fantastic, Anyway, So if I would like to make a table for this, I need to think about it, right? So if I go ahead like this and make a table, I have three input. I have a clock and S and R, right? So I can say here clock and S and R, and I have here Q and Q complement. What I'm building now is called what? The first table out of the three tables.
Truth table.
First table, yes. Then the first attempt, this is like this. That what does it mean? Negative. If there is negative edge going in a positive edge, it will do nothing, right? So pretty much no matter what is SR in this case, I don't care, right? Then when I'm caring, when the positive edge happens. Right? So 0, 1, 0, 1, 0, 0, 1, 1. Then, you know, we have those 4 active states, right? It depends on what latch we have, because this is our latch basically, but you know, it has a timing in it, right? So do you remember the latch table? Somebody remember the latch table? Somebody remember the latch table? Somebody remember the latch table? So what is the latch table?
Memory.
To our memory.
Yeah, we need to go back. I'm not gonna replace it, so I can just go back into the. It was when is the last picture? 29th, right?
Hmm.
No, it's not 29. It was what? 28? Here, right? That was our lovely table, right? 0, 0, unused. 1, 0 is used on whatever, and all these things, right? Everybody agree? So I can take this gentleman and remember how it looked like, and I just use it there.
Mm.
Sounds good? So
Good.
I can go ahead and say, I need this gentleman. So how can I take a copy of it? I don't know if this guy will allow me. So what I can do, I can just this thing is coming to me every day. It's ridiculous. At the same time, you know. What I can do, I can just do like this, because I don't want to actually go and revet stuff from scratch. So I will just go back here and say, you know, I'm in November what?
November 2nd today.
Can you see?
It's right there.
Here. So I'm gonna put here on a side, and I say this is SR, right? This is Q bar complement 1, 2, 3, 4. 0, 1, 0, 1, 0, 0, 1, 1. You know, we said 0, 0 is gonna be what? Not used, right?
Hmm.
Not used. 0, 1 is gonna be 1, 0, 0, 1, and then you know gonna be in memory. Right?
Yes.
Sounds good. Okay. Now move this here. Right? That's it. So that's gonna be your table. Congratulations, you finished. You know, now that looks really fun, right? So in this case, I can come and say 0, 0, 0, 0, not used. 0, 1, 1, 0, 1, 0, 0, 1. Here, memory. What does it mean, memory? That means QN. So QN, it should be the same as a QN. What is QN and what is Q, not QN and what? I will tell you. Here's a story. In the beginning of our discussion about the sequential circuit, we came into fancy circuit, right? That circuit, it was what? It was like a box like this, combinational circuit, right? It has an input, and then, you know, the input use output, and then, you know, some of the output, I want to delay it, and then the delay will go like this. Do you guys agree? Which is opening the door that, you know, if I have a Qn, that means there is Q plus 1, N plus 1. So if I have a Qn, I should have also Qn plus 1. That means the present, and here's the next. This concept we didn't have in the sequential, in the combination, right? So we need to look this this concept to produce the characteristic table or the what? Or the state table, other some books saying that, right? So the second in row will be fantastic table. It has the QN, the present state, with the SR as an input, because look, input with the present state to bring next state. The next state later on is delayed to be the present state and you move forward, right? So S and R, and here we're gonna be QN plus 1, right? This fantastic table, we call it what? Characteristic table. Make sense? Now we created how many? 1, 2, 3. So 3 variable input. How many states we're gonna have?
8.
Thank you. 8. So gonna be 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. Right? Easy, right? When I see SR like this is equal 0, 0, from the truth table, I will take the information. Do you guys agree? So, SR is 0, 0, not used. So I would say not used. When I see it, another 0, 0 here, not used, right? Then if I found SR is 0, 1, if I found SR is 0, 1, it doesn't have any relation with memory, right? So it's gonna be 1, 0, right? So I can find 0, 1, I can see 1, 0, if I would like to say, it's gonna be 1, basically. Here gonna be 1, right? You can actually make QN plus 1 complement if you want, it's up to you, I'm just looking for this one for now, okay? Then I can look more forward to 1, 0. 1, 0, I find it here 0. So it's gonna be here 0. So 1, 0, 0, 1, 0, 0. Look at the crazy thing. What? The 1, 1, it will be memory. So that means the present will be the next, right? So I look, 1, 1 here. The present is 0, so the next is 0. 1, 1 here. The present is 1, the next is 1. Would you imagine what I did now? I finished the state or the characteristic table of who? SR flip-flop. Any question?
Not yet. I think I'm good.
So somebody can ask you, is it possible for you to implement this table? K-map, you finish. How are you gonna make K-map and not used? I can say I don't care.
Oh, so for the not used state, if we were to do a K-map out of this, we would use X or X.
X, or I can make it Z or anything is floated. I cannot.
Don't care.
Right. So this one is a little bit tricky, because sometimes you don't care, then you can destroy something, or something, But at least you know those, right? So what will be the next after that, from your point of view? It will be the third table we talked about. Do you guys agree? What is the third table we talked about?
Excitation table.
Excitation table. So the excitation table, they have set of inputs and set of outputs. Guess what is the input? The present and the next state are the input, and the output will be the next input. Because you look back, right? So it's gonna be what? It's gonna be QN plus 1. So the present and the next state will be deciding what it will be the input, right? So it's gonna be here S and R. So in this case, you're gonna make what? 1, 2, 3, 4, right? How many states do we have? 1, 2, 3, 4, 1, 1, 1, 1. So 4, right? How I'm gonna fill this guy? From where? From the state table. Let's make it, let's think about it. So Qn is equal 0. Where is Qn is equal 0? Here is Qn is equal 0. Here is Qn is equal 0. Right? Qn plus 1 is equal 0. Where Qn plus 1 is equal 0? There's u here, there is u here, right? So it's basically, it's in this case and this case. Right? So I can literally make a different color here and say, this is the state and this is the state I'm looking for. You guys agree? The rest of the nation agree?
Yes.
In that case, I will look to my SR, my lovely SR. I found my lovely SR. S in the first is 1 and the second is 1. So basically, no matter what, it's going to be 1. So I can just write here 1. That's it? Nope. R is 0 in 1, but R is 1 in the second. So basically, it can be 0 and 1. So I can just translate it to X. Then I can just go ahead and have a different color. So Qn is equal 0. And Qn plus 1 is equal 1, right? So Qn is equal 0. So this guy. And Qn is equal 1 here. Anything else that has 0 and 1?
No, I think it's just that.
This is the only one, right? So in that case, I can take this guy literally like this. It's going to be here 0, 1. Then let's have a different color. We are looking for 1 and 0. So 1 and 0, this and this. All right? So in that case, it's going to be 1, 0. Then I'm looking for the last one, which is 1, 1. 1, 1, 1, 1, 1, 1, 1, 1, 1. So it's here and there. And it's in here and there. Right? So here is 1, here is 1. So that means R is equal 1. Here is 0, here is 1. So that means S is equal X. I have a news for you. We finished SR flip-flop. And it was my pleasure to finish it. So did you see, you know what we already have done? It's
3 tables.
Yeah, I mean, you understood very well what is latch you are done. You understood what is understandable of the trick of the clock you are done. Would you imagine? So implementation is a piece of cake, right? Implementation is very easy, right? So if somebody tell you, can you please implement for me this? That's like, you know, you are playing basically, right? So pretty much, you know, implementation, it's gonna be here my flip-flop like this. Here is my Qn. Here is my Qn complement, for instance. You know, here is my S, here is my R, right? And here is my clock, right? S is 1, 1 here. So pretty much you are talking about Qn plus 1 or something, you know. You can make any implementation you can imagine, you know. You can use the truth table and you implement whatever you like to implement, you know. Make sense?
Yeah.
Is it clear to everybody in the nation?
Very.
Implementation is basically pretty much straightforward, right? I would assume that you understand what I'm saying about implementation, right? You're gonna make a K-map and then, you know, you will finish the whole thing and then, you know, you will just loop back. That's it, right? Okay, let's see what people saying here. Everybody's saying yes, that's amazing. You know, that means I'm winning. Yeah. Okay.
However, I do know how I would do it. However, I would appreciate an example, and the reason why is just so that I can.
I can make it. I can make it. It's
Yeah.
It's a piece of cake. You know, it's a fantastic piece of cake. So let me find you the right implementation. It should be here. So let me see, because I would like to show you the thing as it should be. And if I like to implement this, basically I would say my SR is coming from the Q, right? So this I have like this, I have 1, 2, 3, 4. I have here the QN plus 1, 0, 1, 0, 1, 0, 1, 2, 3. So I'm talking about, SR is basically location 0 and location 0, 1, 2. It's going to be Qn plus 1, right? So Qns is basically Qn plus 1. So you can
So
just
can I pause you for a second?
Huh?
Pause you for a second with a question.
Which one?
Okay, so I just wanted to make sure, and this is kind of was my question. For the implementation with the flip-flop, in this case, use the excitation table, correct?
No, you can also make an implementation for the characteristic table because that will be later, or the state table, because that will be later actually building something that's called a state diagram.
Oh, okay. Thank you for that.
Okay, I will tell you about the state diagram soon, but anyway, I will just put this in aside now so I can finish the rest of the flip-flops, because the implementation itself is more fun when you will move from flip-flop to another one. It will make more sense, than just like implementing the SR itself. You know what I mean? So the SR is SR, just a flip-flop and that's it. That makes sense? Anyway, I would like to understand if all of you understand now what is the whole entire trick of the SR flip-flop. And everybody understand that also, the problem of SR flip-flop is standing in what? Unused state because of the problem of what? Huh?
No control.
Exactly.
Yeah.
Exactly. Now let me go into the second gentleman. It's called JK flip-flop. So the JK flip-flop, it's the one figure out a solution for what?
For the not used state.
For not used state. Exactly. How are we gonna deal with this? It's really straightforward. So basically, here is my JK. It looked like this K, and here is basically the Q bar, and here is the thing. Okay, sounds good. There is a story behind it. Basically, that was built in the top of the SR. That was built in the top of the SR for a reason. Okay, there is a crazy reason for this. So if you look to the JK, the guy who built the JK, he came into the point say that if you have an S like this, an R like this, what I want to do something crazy. And what is this craziness thing I want to do? I would like to get to the point that I have AND gate and I will take the complement of it and I take it like this and I bring J. Then I will take this one and I will go like this and I will just go ahead and do like this, and that will be the K. Why he did this? He tried to build something more stable, which gonna make me use what? The last state. Make sense?
Yes, I see.
Professor, but everything is still the same otherwise, right?
Yeah.
It's just that he had these.
Yeah, he will clock and then we done.
Yeah, okay.
Yeah. That was the first attempt that guy wanted to do, So he came into this point. He said, you know what, guys, I'm tired of this. That's really crazy. I cannot live my life like this. But of course, it's gonna be also NAND. Don't forget, because we are using NAND on building the latch itself inside the SR, right? So we are following everything with NAND. Make sense? Also, if you like to add the enable, which later on will be the clock, right? So you can do it also like this. They call it tick. What do you mean by tick? That means that every single tick some movements happen between the input and output. You can call it enable, it's up to you. There is no problem, you know. So, or they call it what? Toggling. So toggling or what? Toggling or what? Huh? Toggling or what?
Enable.
Enabling, yes. Or triggering. So pretty much I can come and say my JK circuit looks weirder. What weirdo? It does look like this. All right. Then I can just go like that. Right? Then it looks like that. Then I do like this. And that's gonna be my clock. While there is here J, while here is K, and that guy said, you know, looping back with the invert of the state will solve my problem. That was his assumption, right? So he came into the point, taking this like this, and he came into the point, taking this like that. And he called the whole entire thing in front of you what? JK flip-flop. Sounds good?
Yes.
Now we need to see what is the fancy thing that he has done. You know, I have no idea. It doesn't look really fantastic to me because you know we will see there's a problem and then you know I will fix the problems here. So that was the first attempt of building the JK flip-flop. And we will come into the risk condition problem. Then you know I will show you how he fixed the risk condition, and from there we're gonna bring the characteristic table and excitation table and all of this yada yada yada. That sounds reasonable to everybody?
Sounds good.
Okay, so if I want to see the table, here's the Q bar, right? I need to see what will be the input here, right? And we can try to play with the input and see whether they're gonna be working or not, right? So I have to build a table saying that, you know, I have a clock and I have a J and K and I have a Q and Q complement, right? So in that case, I know the enable is low, right? So if I put here 0, for instance, what will be happening? If you have NAND and one of the input of the NAND is 0, what is the output should be?
0.
You think?
1.
No, I don't think so. We should look. If you have XY, 1, 2, 3, 4, 0, 1, 0, 1, 0, 0, 1, 1, and then you know you already have Z, right? That's and flipped. So and that means you know 0, 1, 1, 1.
1.
So I have input 0. No matter what is the second one is 0 or 1, the output will be what? 1. So in that case, this guy will be 1, this guy will be 1. If inside this NAND, 1, 1 happens, right? So what will happen?
Memory.
We can check the table, right? So the table was in the latch. 1, 1. It's a memory. Memory. Sounds good. Then you're gonna move forward. Say 1, 2, 3, 4. I'm going up. I'm going up. I'm going up. I'm going up. 0, 1, 0, 1, 0, 0, 1, 1. Then we'll move forward, right? So I have 1 here. Now, right? I will clear up these 2 1s. Then, you know, I have 1, 1, right? And also I have my JK 0 and 0, right? So 0 ended with 1. What is the output will be? 1, right? Do you guys agree? Anything
Yes.
ended with 1, what the output will be?
0. Oh, wait, no.
Should be 1 unless it's 1.
Right? If it's 0, it will be 1. If it's 1, it will be 0. Right? Do you guys agree? So in that case, it depends on the Q, right? So, think about it, right? If it's 1, if it's Q here, Q complement, right? So that means I'm actually getting Q. All right? And if it's Q here, it's gonna be Q complement. Because Q complement is gonna be Q, right? Then you will move forward with your statement. So does that make sense to everybody? What do you guys think?
So I'm getting Q from the cycling. I don't know. What do you call it? The feedback from
So basically it's a memory.
Yeah, the memory. Okay.
Because it's actually storing itself as itself,
Okay. All right. Yeah, it's storing it.
Twice. Is it clear?
So it doesn't have a not used condition anymore.
Yeah. We're gonna continue. We'll see what will happen now. The not used condition is not coming because now I'm using everything in NAND and NAND, Anyway, now we're gonna move to the 0, 1, 1, 0 and see what will happen. Look at this, 0, 1, right? So I'm gonna clean up my situation here, right? So J is 0, right? K is 1. So I'm gonna have it here, it's equal 1. Oh, scheiße. 1. So K is 1, J is 1, right? Let's count. So what will be? So J is 0, and we have 1. Any 0 with 1, the output will be 1. So gonna be 1 and 1. Anything 1 with the Q, it will be what? Q complemented. So basically, you're gonna flip. So gonna be exactly like the truth table, right? Of the SR, right? So when it's 0, 1, it's gonna be 1, 0, and here it's gonna be 0, 1. Because still SR, right? You just play with SR. This part is the fun part. This one especially is the fun part. This one, it was the not used one. That was the not used one. Don't worry about the SR now. I'm looking to this, right? Why? Because do you remember in the beginning of the end of the last lecture, when I put this NAND was enabled, what happened if things got flipped? You remember? So this one, it used to be not used. Right? Let's see what does this will look like now. So we're gonna clear up everything and we're gonna put it with numbers. So imagine Q is 0 and Q bar is 1. Look what's this, okay? Imagine 0 is 1, Q is 1, and Q bar is 0, right? So I'm gonna take this Q here to be 0. I'm gonna take the Q bar to be here is 1. Do you guys agree? Okay. Now, J is equal 1. K is equal 1, right? Enable is equal 1, right? Is there a ton of ones coming? So this one will be what? When NANDed with 1, what is the output?
0.
0.
That 0 NANDed with 1, what the output will be?
1.
Right? Because 3 NANDs, it will reduce what? NAND pass it to NAND, right? You guys understand what I'm saying? Is it clear? So that means here I have what? 1. Then same thing here. Here is different a little bit. 1 with 1, what is the output? 0. 0 with 0, the output will be what? 1. That makes sense? Now, I have here 0, and I have here 1. 1 with 1, the output will be what?
0.
I think there is something mistaken here. So one second. Let me see. Again, 1, 1, 0. If you add all of those guys together to be what? 1, 1 is 1. So 1 with 0 is gonna be what? 0. If you flip it, it's gonna be 1, right? Then this 1. If you add 1, 1, 1, it's gonna be 1. You flip it to be 0. I'm sorry. Okay. Then 0 go in here and 1 is going here. 0 is 1 or 1 is 0 gonna be here 1. And there it's gonna be 0.
So at any one point in time, it can either be on set or reset.
Yes. Let me show you. Then if you move the iteration again, they're gonna be 0 and they're gonna be 1. If you move again in iteration, they're gonna be 1 and they're gonna be 0. So pretty much, this case is actually QN complement.
Professor, I don't get that. You're adding the same numbers together and you're getting a different answer. I don't understand that.
Wait, what happened?
So you're putting 0 and 1 into that NAND gate and you're getting 1, but then you're putting 0 and 1 into the bottom NAND gate, you're also getting 1.
Because it's the next, the previous was 0, 1, but then your next will be the reverse. Because there is a timing here, right?
Yeah, there's timing.
You understand what I'm saying, right? So the first input, it was 0 and 1, right?
Mm-hmm.
After you do this flipping thing, you know what is the output. It will be something else. Then you will take that something else and it's gonna push it as an input. Then what will be coming, something else, and so on. So basically, if it's 0 here, 1 here, next it's gonna be 1 here, 0 here, next it's gonna be 0 here, 1 here, next it's gonna be 1 here, 0 here.
All right.
You got my point? So pretty
Yeah,
much, if you have here a clock, this is my clock, right? And then, I found out J is 1, K is 1, right? The Q, it's basically, let's say it's QN, it's gonna be QN complement. So let's make QN a shape. Just give a shape for the QN, right? So this QN, for instance, is basically was like this. Okay. Then I need the QN plus 1. In that case, it's coming from the output here. So I look at it, right? 1, 1, and I have here 1. What will happen with this? It's gonna be doing like this. So when the positive edge with the high level with a positive edge happening, this thing is gonna be rippling. It's gonna be toggling like crazy. Toggling like crazy until you will go in a low, then it will stable. Then you will go in a high, then it will be like doing like this. This toggling is called triggering really high or risk condition. Okay, so they said if you would like to solve such a kind of problem to make JK is more stable and to make it actually pretty much QN, but fixed, what you can do is actually to have 2 latches. So you're gonna have 2 latches that basically know the concept. What is those 2 latches are doing is doing the following. So the first latch is like this, right? We have here, that's coming from the Q, that's basically the J, and that's basically the second one is the clock, and here is basically the clock. And here is going to end, here is going to the end. They're gonna be like this, and then from there you go like that, and then from here you can go like this, right? So this is the first latch. Then have you finished? Oh, we haven't finished. So basically, you have to go into the next stage. So they call this master latch. Look at the next latch. The next latch is a little bit crazy. Why is it a little bit crazy? Because you're gonna go ahead and do the same thing as you did it here twice. So basically you already have here K. So you're gonna make also here NAND gates, here's NAND gate, and then you already have here your latch, and then you already have here the Q, and here's the Q bar, and then you will take the Q there, and you will push it here, and you will take the Q bar, and you will take it there. Is that set? No. The end of this will be the negative of the clock.
So
basically you have two latches, right? One is working in the positive edge, one is working with the negative edge. So pretty much, what does it mean? It means that instead of rippling like this, no, it will be flipping every positive edge. That's it. It will be just flipping every positive edge. How? So here is this positive edge. I found the QN is high, right? So I will just go and make it low. Then low, high. No, nothing. It's gonna be low. Here, I found it high. I'm gonna be also make it low. Then I move here. I found it low. I will continue. Imagine that I just considered to make it high like this, right? So what I'm gonna do? Okay, I will just continue with my clock. So okay, I find here positive, right? And I find it high, gonna be low. Then I continue. Then I find it, for instance, in a certain time low here. So here, I find it low. I can decide to make it high. Then I move to another positive edge. I find it high. I'm gonna make it low, and so on. So now every single positive edge, it will be deciding to queuing and it to inverting if you have the J and K just one. Is it clear to everybody? Hello.
Yeah.
So everybody think it's easy peasy lemon squeezy?
You're just adding another latch, yeah.
Exactly. Exactly. So pretty much you can come into a very nice conclusion. Same truth table. Here, J, K, and then clock. Then you have here Q, right? So you can come into the conclusion. If it's high, I'm gonna continue to be what? Qn. This is n plus 1. If it's 0, and then if it's 1 0, whatever 1 0, I mean whatever, I'm just making a table, right? So basically gonna be here 1, it's gonna be here 0. When I see this, it's gonna be what? And we call it what? Toggles, right? So from there I can make the state table, right? So my state table is like this: Qn, Jk, and Qn plus 1. 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 2, 3, 4, 1, 2, 3, 4, right? Then I look. When Jk is equal 0, where is my Jk is equal 0? I'm pretty much Qn. So I see my Qn. Oh, you're 0. Stay. You're 1. Go 1, right? Then I see that, Jk is 1, 0. Where's my 1, 0? 1, 0, 0. 1, 0, straightforward 1. 1, 0, straightforward 1. Then I find it is 0, 1. Where is my 0, 1? 0, 1, straightforward 0. 0, 1 is straightforward 0. Then I found it 1, 1. Oh, 1, 1. Where's my 1, 1? 1, 1 is Qn complement. Here is 0, so it's going to be 1. Here is 1, it's going to be 0. We finish the state table or the characteristic table. Then let's make the third table, which is the excitation table. So I will look to my excitation table, see Qn plus 1, Jk 1, 2, 3, 4, 0, 1, 0, 1, 0, 0, 1, 1, right? And I will take it from this, right? Let's have a colors. So we said Qn is 0. Qn is 0 here, here, and here, and here, right? I'm looking for the Qn plus 1 is 0. So here and here. So in that case, I'm looking for these two guys as a case statement, right? So my J is 0, 0, so 0. My K changed from 0 to 1. That means I don't care. Make sense? Then I go into the, when is Qn is 0 and is 1, 1. So I'm talking about those states. So there it's basically 1, 1 in J, and the K, it will be X, I believe. Then I move to 1, 0. Where's my 1, 0? So 1, 0. Is there any 1, 0?
The last one?
Yeah, here. So 1, 0. So it's basically 1, 1. So gonna be here 1, and here is basically 0, 1. So gonna be X. Then 1, 1. Where is my 1, 1? 1, 1 here, 1, 1 there, 1, 1 here, 1, 1 there. So that was 0, 0. So gonna be 0. That was 0, 1. They're gonna be X. Imagine we finished the excitation table of the JK flip-flop. Simple.
Professor, can you do 1, 0 one more time?
Sure. There's no problem. What we can do, you want which one?
1, 0.
This one?
Yes.
1, 0. Okay. Where is 1? Here. Where is 0? Here. Right? Is there any 1, 0 again? Here. Do you agree? Right?
Yes.
Yeah.
Yeah.
So which one in front of here is basically 0, 1, right? 0, 1. Here is 1, 1. Right? So here is 1. Here is X. Make sense?
Yes. Thank you.
You are most welcome. Any questions so far? Any problems so far? I can tell you a story, but I'm not going to go too much in details. The story, if you understand JK, we are done with the course. Why? Because, if I go ahead and bring the J and K and I take it like this, so pretty much I'm actually doing what? I'm doing something fun, which is basically neglecting all of the 4 statements, all of this 4 statement into just 2 statements.
D
Right?
flip-flop.
Yeah, and this gentleman is the D flip-flop. Or I can bring the JK and I take the J and K and connect them like this. Which is basically killing the whole entire JK and take this state and this state. So that means, I store or I flip the store.
Oh, snap.
And I can make the table of those next time if you want. But, in general, I have a news for you. We finished the flip-flops. What is our expectation now is actually moving from one to the others. And that can be our next what? Lecture.
Professor, which chapters are included in the quiz?
Everything.
All right.
Okay. It's a quiz, it's not like heavy as the midterm should be. Okay. Any questions?
Yeah, Professor.
Yes.
I'm gonna get my snipping tool out. Can you go back to the other one, the second one, the JK flip flop, the one where you added another latch or another clock? That one right there. I'm gonna get my snipping tool out. There's a lot of drawing. I'm sorry. That's crazy.
Yeah. So basically, this is the latch for the positive. It's working with positive, right?
Mhm.
Look, this is the latch is performing with what? Negative of the clock.
All right. Okay,
And they're
thank you.
passing to each other. That means one is working in on, one is working in off. One is working in on, one is working in off. The whole idea is actually to what? To completely resolve the problem of what? The risk condition. What does risk condition mean? That means, when the high of the JK happened, the QN will be coming here into the point of rippling. That means it will go like this. That can cause a device damage.
Mm.
That's why they wanted to fix it. So instead, it will be flipping every edge of the puzzle.
Awesome.
Sounds good? With practicing next time, it's gonna make it a piece of cake. And moving from one to the other is gonna make it also a piece of cake. Sounds good? I would say thank you for attending this course. Thank you for attending this class. And it was my pleasure to talk to you today. I would say stay safe, God bless you, and I will see you on Wednesdays. It's gonna be 8 a.m. in the morning. I'm gonna release the quiz. You have up to the midnight. If you have any questions, ask me. And I might, I will cancel the class on Wednesday, so you guys will just focus on what solving the quiz, so you can have your time, because it's gonna be 8 o'clock, 7 o'clock. You're gonna be tired, so it's better for you to deliver earlier than midnight. Makes sense?
Okay, thank you.
You are most
Thank you.
welcome, and I think that would be more better for you guys. I don't want you guys to overwork and tire yourself. Okay. God bless you. Stay safe. Okay.
Thank you, Professor.
You
Have a
too.
good one.
Thanks,
Thank you. Bye-bye.
Professor.
God bless.
One, I'm gonna reply back soon. Okay. Thank you.
Okay, got it. Sure. Thank you.
Bye, guys. Thank you. Bye.
Bye-bye.